This video goes over some binomial distribution examples from the Winston and Albright textbook. The first one is that we're testing some batteries, and we tested 100 of them, and traditionally we think that the probability that one working is 60%. So out of 100, we would expect 60 of those to be working. So the question though is what is the probability that we would have exactly 58 working out of 100? The formula that we're going to code up is equal to binomial.dist, and you put in 58 out of 100.6, and the last argument is 0 because we're looking for an exact. So here, binomial.dist, our 58 out of 100, probability of success is 1, and we put a 0 in the last argument because we're looking for an equals, not a cumulative. So it's about 7%. The next one is a probability that we would have 65 or less that are working. Equals binomial.dist, 65 out of 100, probability of success is 0.6. Now we're going to put a 1, because we are looking at less than or equal to, it's a cumulative. The next one is a probability that x is less than 70. Well, how we were going to solve for this, since we got a strictly less than, notice the difference between this one and this one. So when you got a strictly less than, you need to replace this with probability that x is less than or equal to 69. These are equivalent statements, and we can code that one up. Binomial.dist 69, or if you want to be real picky, 70 minus 1, so you know where that 70 originated out of this many. Probability of success on one trial, and the last argument's 1 because we have a less than or equal to. This one is greater than or equal to 59. That's on the right hand side, so we have to subtract it from 1 first, and the probability that x is less than or equal to 58. So look how that works. Greater than or equal to 59, 59 or bigger, is 1 minus 58 or less. 1 minus binomial.dist. Put in your 58 out of 100.6. The last argument is 1 because we're looking for a cumulative. To estimate the mean and the standard deviation of a binomial distribution, or there's no estimate, this is what it is. It's equal to how many we chose. Excuse me, this should be, this is uppercase N. And this is also uppercase N. So the expected number that we would have working is this times this. Very easy. The standard deviation is actually pretty easy too. Square root of this times p times, in parentheses, 1 minus p, and close out the square root. That's that. Okay, that's example 5.7, or part of it. Example 5.8 is an interesting problem. Someone has solicited you and asked you, or says, "Hey, I'm a good stock picker. I can pick stocks real well, and you should buy my answers. If you buy my picks." And their evidence is that they have a stock that has been successful. That he's correctly a stock that has beaten the stock market 37 times out of the last 52 weeks. So this particular stock has been successful at beating the stock market 37 times out of 52. Now, that's possible of happening by chance. You could pick a stock and see if that stock every week does it beat the stock market. And this one beat it 37 out of 52. Well, what's the likelihood that would happen by chance? By chance, it's just a 50-50, so it would be equal to 1 minus binomial.dist of, excuse me, let's do it this way, less than or equal to 36 equals 1 minus binomial.dist 36 out of 52. The probability of success just by chance is 50-50. And I'm looking for a cumulative. Look at that. That's very unlikely. The likelihood that that's going to happen is very, very small. So it looks like that the chance that you could pick a stock that could win 37 or more out of 52 times by chance is really, really unlikely. So probably you should listen to this guy. But wait a second. Remember, he's got thousands of stocks to choose from, and he just needs to find one to try to sell you on this concept. So let's say that he's got a pool of 400 he tracks every day. What are the likelihood that he can find one stock that's going to beat the stock market 37 out of 52 times out of a pool of 400? So probability that just one of this pool, and 1 minus the probability that x is less than or equal to 0 equals 1 minus binomial.dist 0 out of 400. Probability of success is very small, but we're choosing from 400, and it doesn't make a difference. You can put 1 or 0 in this last argument. Well, look at that. That's not that hard. I mean, he's got almost a 50-50 chance just to find out a pool. Let's say, and again, let's say he had a pool of stocks he was looking at that was 4,000 stocks. Well, he's guaranteed to do that. So this is a scam. He's using some type of trickery to try to get you to buy his advice. The last question is using the exponential distribution to overbook, talk about overbooking. So we have flights, and when you book a flight, there's always a chance that people don't show up. And let's assume that the chance that someone doesn't show up is 10%. So they bought a ticket, you're putting people on a plane, and the plane holds 200, and there's a chance that someone doesn't show up, so that plane leaves with 199. Now, you still got their money, but that's one seat you could have sold extra. So, how many tickets should you issue? Should you issue 200? Well, if you issue 200, what's the likelihood that you're going to have a no-show? I mean, that you're going to have more than 200 people show up. It's equal the probability that x is less than or equal to 200. Excuse me, 1 minus that. Well, if you sell 200, the likelihood of that is going to be really small, like 0. Probability, it's binomial.dist, where we put in 200 out of 200. Number of successes, yes. Trials is 200. The probability of success of them showing up is 90%, and we do 101. So, but what if we sell more than 200 tickets? Our plane holds 200. What if we sell more than 200? Let's say we sell 201. Well, then there is a chance that we're going to overbook a flight. It's still very small. Let's show it as a decimal. Show it as a decimal and put some way out there. So the likelihood we're going to have to deal with an overbooking situation is still really small. So maybe we ought to sell 202. Still really small. What about 203? So, oops, didn't do that. Sell 210 tickets. Uh-oh, now we're getting into something. If we sell 210 tickets, we're still less than a 2 out of 1,000 in overbooking situation, so maybe we ought to sell 220. Oh, that's probably too many. That means 30% of the time we're we're going to have an overbooking situation. So we don't want, that's probably too many. Maybe that's about right. That's about 5% of the time are we having to handle an overbooking situation. And usually overbooking means that we start having to offer free flights for people that are there to wait for the next available flight. So how often do you want to handle that process? We know the answer is not 200. We need to overbook it. The question is, how many should we overbook it? And if I had to guess, I would say it'd be around 215 or maybe a little bit less. Yeah, maybe 213, something like that. Whoops. Maybe something around there, between 210, 215. Okay, that should be enough examples of application of the exponential distribution.